Now, if you just came into this room and think regex, I want to kind of set the tone for this talk with a 22-year-old quote. Some people, when confronted with a problem, think, I know, I'll use regular expressions. Now they have two problems. This was said by Jamie Savinsky 22 years ago. Jamie used to be an engineer at Netscape and later Mozilla. And at the time, the hot new glue language or scripting language around was Perl 5. And if anyone has ever worked with Perl 5, it has some awesome regular expression capabilities. But it's also maybe the most unreadable language in the entire universe. And this was sort of a critique of this, right? You get into this mode of Perl being really, really useful with its regular expressions to the point where you'll use regular expressions for anything where you really shouldn't. All right. In this session, we're going to try to understand what regex is, what it does, and more importantly, how. It's not so important for applying these lessons, but I think I'm curious about these things, and since you're here, you might be curious about it as well. And then we're going to have some fun with regex and PowerShell. Sounds good? All right. You might have noticed on the first slide it said regex 4.0. This is not a version reference. If anything, it's a version reference to this talk. I've talked about regex at this conference previously, and so this is sort of an iteration of my understanding of what regex is and what we can use it for, and hopefully you'll get something from that as well. So today we're going to try to cover what is regex. We're going to do a little recap of kind of the origin both of regular expressions and this talk. We're going to have like a very quick, like a deep or introduction into regex in PowerShell, how we can apply this. Then this year I want to talk a little bit about regex and runtime performance, and then just like the previous 2 years, we're going to dive into some real life examples of some code, see if we can find some regex solutions to some of these problems, and then maybe build some cool tools. The thing is, I have what they call galloping ADHD, and I'm really bad with these sort of linear structured narratives. So I thought, instead of waiting with all the code until the last, we can kind of start looking at some regex already. So I transformed this agenda slide into regexes instead. And I think this actually way better describes what we're going to talk about in a second. The last piece, regex and performance, in order to kind of get into that, we also kind of have to get into understanding how regex engines work. So we're going to try talking a little bit about that as well. Right. First off, what is a regex? What is regex? If you search any variation of a string that might match this regex pattern on the internet, you might find answers like regex is a pattern matching engine, or regex allows us to apply search patterns, or if you dig deep enough, maybe not even that deep, regex is awful, right? This is not helpful. You've come no closer to understanding what regex really is, right? So the most succinct way I think we can talk about what regex is. Regular expressions describe regular languages. Now, talking about regular languages doesn't really make sense in the context of kind of modern programming languages and modern application of regular expressions. And you may also be sitting there thinking, what the hell is a regular language? I speak a language, isn't that regular? So instead, what I'm going to leave you with is that regular expressions describe the contents of strings in the context of computer programming and PowerShell specifically. Right. So a regex or regex, non-counted, is basically a meta language describing other languages or describing text. When we refer to a regex, we usually refer to some string of syntactical elements from this meta language, right? You have maybe some normal characters, then you have all of these weird squiggly meta characters at the top. And then regex engines, these things that we built in existing frameworks and programming languages, apply these expressions in various operations, right? So you can find things, you can split strings, you can replace strings. Right. About the origin of this talk, I went to PSConf EU in 2016 for the first time. It was a great experience. I ran into Øyvind Kallestad, And he gave kind of a regex 101 talk in PowerShell. And this was great, but he came up with some of these regex constructs that he thought, oh, maybe you should learn this. And he didn't really have any good examples. And so I started heckling him. And he kind of called me out and he said, either you quit this or you get up here and answer your own questions. And I said, okay. And by the way, you're giving this talk next year. So next year I gave sort of a similar talk, but with more real life examples. So if you want to improve your regex chops, I've learned a lot from this. You deliver regex 5.0 next year. This is an open invitation. All right. On the origin of regex, regex or regular expressions, as they were called at the time, is a concept conceived by a mathematician and linguist, I think, Stephen Kleene. This is also generalized. There's a generalized mathematical concept where you basically apply the same constructs of regular expressions to a mathematical set. This is known as Kleene algebra. I've been saying Stephen Kleene for the last 3-4 years, and I was recently told that he actually preferred to be called Stephen Kleene. So this is actually called a Kleene algebra. You learn something new every day. Regular expressions in the context of computer programming saw kind of adoption in 1968. Ken Thompson, who was working at AT&T, at Bell Labs at the time, he was working on this editor, ED, right? One of the first kind of smart code editors, and so he implemented this global regular expressions pattern, as I believe. This is kind of where the name grep comes from. And so he implemented this in the editor, and you might ask yourself, why would you come up with something like regular expressions in your editor? Well, the thing is, this was in 1968, right? And if you look at the history of Bell Labs, the next 5-10 years, they invented things like C, Unix, all these huge code bases where you had maybe many repeating symbols that you would need to refactor at some point, or you would need to find where in the code did I leave this subroutine. And so it kind of makes sense to have something where you can go in and describe some sort of string that you're looking for, and then do replacements or similar on. Regular expressions saw a wider adopted use as part of Perl and Tcl in the late 80s. This is where regular expressions, as we kind of know them today, diverged a little bit. Perl adopted sort of its own syntax, its own meta characters in the way we describe our string patterns, while Tcl kind of stuck with what was already known from Unix. So some POSIX standards exist for regular expressions, but Perl 5 syntax, or something that looks like Perl 5 syntax, is kind of the de facto standard today because of something called PCRE, Perl Compliant Regular Expressions. Perl Compliant Regular Expressions is a C library that was written in the 90s for other languages to implement regular expression features that would kind of be one-to-one or almost one-to-one with what you would find in Perl. So if you can do something in Perl, all of a sudden you can do this in Java, you can do this in C++, you can do it in a bunch of other frameworks. And so this way, Perl syntax kind of became the dominating regex syntax. Right. As promised, we're going to look quickly at regular expressions in PowerShell. We have a couple of different options for how we want to apply regular expression patterns. First of all, I want to highlight select string, the commandlet. Select string takes a bunch of strings on the pipeline and applies a regex pattern to it, and then it outputs some information about whether it matched, and we're going to talk about what that means, matched this pattern against any of the input strings. This works on files as well. You can take the output from getChildItem, pipe it straight to select string. This is usually faster than saying than doing get content on a file and then piping the strings directly in. Or you can specify wildcard path, and select string will gladly take that as well. We also, we also have some built-in operators in PowerShell that allow us to apply regular expression patterns. In kind of the first example up here with the match operator, we have the string some stuff. We apply the match operator with a pattern stuf plus. Plus means one or more. It's known as a quantifier, and then at the end we have a $sign. Now there's no $sign in the string some stuff, but dollar is also a meta character in most regex flavors, and it means end of string. So basically what we're looking for here is a string construct where we have the letter S, the letter T, the letter U, the letter F one or more times, followed by the end of the string. And so this is going to return true because the last 5 characters of this string, S, T, U, F, F, and then the position at which the string ends, matches this pattern that we've specified. Dash match, the operator, also has this kind of magical feature where you can use something called named groups in your regular expression patterns, and PowerShell will kind of pick up whatever you captured in the input string. So in this case, we have the same pattern, but preceded by this weird construct that says open parenthesis, question mark, angle brackets, and then inside the angle brackets we give it a name. This is the name of the group. We call it my group. And then we have a pattern before that sort of sub-expression ends, which is dot star. Dot means any character but a new line, and star means 0 or more times. So here we're interested in matching a string where something occurs, then there's a space, then the pattern we saw before that'll match the end of the string. And so here, if we apply the match operator and then reference matches, which is an automatic variable, it's a hash table, you can index into that by the group name, and it's going to tell you exactly what it matched. So in this case, it's going to say more, because that was what was in place for the kind of pattern that we named my group. Match also works as a filter operator, like most other comparison operators in PowerShell. You supply a list or an array on the left-hand side, and it's going to give you back copies of whichever strings on the... Yes? Should the return be more with space or without space? I think this should be without space. This is a typo on my part, because as you can see, there's an explicit space outside the sub-expression. So good catch. Excellent. We have our next speaker. Yes, yes. The curse has been lifted. All right. Other than the match operator, which works both as a filter and as a scalar comparison, we also have direct access to kind of the underlying framework class library that contains all of this regular expression magic. Since PowerShell 2, I think, we've had this type accelerator regex, lowercase, and this references the regex class that exposes all of these operations that we can do with regular expressions. The simplest one, which is kind of comparable to match in scalar mode, is match. We give it an input string, we give it a pattern, and then it simply tells us whether that pattern validly described the string we gave it. Finally, since PowerShell version 3.0, we have 2 new native operators. They're not really new anymore, but we have two native operators, dash split and dash replace. Dash split also takes a non-regex construct, but we're not gonna go into that. Come ask me about that later. What it does take is a regular expression on the right-hand side, and then it's going to see if it can find that pattern, right, that substring within the string that you pass to it, and then split at that point. And so in this case, where we give it the string 2, many, commas, and split it by a comma, we're going to get an array of strings back, the first string being 2, then many, then commas. Similarly, we can also replace patterns that we can describe with another piece of text with the dash replace operator. So 2 space many spaces dash replace on \s. \s is yet another special or magical kind of meta character in regex. This is a construct that means white space, right? So any white space character, this /s construct will match that. So in this case, it'll match the spaces before and after many. And if we attempt to replace it with a comma, we're going to end up with a string similarly to the one we had before, where the words are delimited by commas rather than spaces. As I was saying before, we're going to talk a little bit about regex and performance. A lot of people ask about this. Can I make them faster? I see there's a compile flag. Can I compile my regexes and make them faster? The short answer to that is probably not. Regex and performance, there's a bit of a weird relationship here, depending on how the regex engine that you're working with is actually implemented. Because a lot of things go on in the background from the time you give it a pattern, have it match some strings or do some operations, and then to what actually happens like inside your computer, right? And so in the case of .NET, in the case of PowerShell, the regex engine here, performance has very little to do with the length of your pattern strings, right? I could supply a regex pattern that is 100 characters long, and it would maybe perform just fine. It also has little to do with readability because they're all unreadable, so that doesn't really factor into it. In 2016, when I first gave this talk, I gave the introduction of a story that kind of impacted me personally. As some might know, I'm kind of addicted to Stack Overflow, and Stack Overflow went down one summer. And this is what they wrote in their post-mortem. We experienced the 34-minute outage starting at 14:44 UTC. The direct cause was a malformed post that caused one of our regular expressions to consume high CPU on our web servers. Notice here that what they attribute the cause of this outage to is a post, so some input string that they're trying to apply regex to, rather than the regex engine or their regular expression itself. They're attributing this to the input. As some of you might know, the regular expression that got embroiled in this whole outage was fairly simple. It looked like this. Here we have a caret at the start. A caret outside any grouping construct means start of string. Then we have these square brackets in which we have two elements. We have /s, like we saw before, any white space character, and then we have a Unicode character. I don't know which one it is, but a Unicode character. So we'll be looking for one or more of any white space or this specific Unicode character, or we will be looking for the same thing followed by the end of the string. Now, okay, if you think this is a little ugly and unreadable, I'll tell you, the exact same thing would have happened. The exact same outage would have happened had it looked as simple as this, which is a pattern you might have seen before. Significant performance impacts on the regex engine, at least in the case of .NET, is the length of the input strings, and then something I would attribute to greed and ambiguity. This is not greed as in some sort of moral question, but as in how greedy is the regular expression engine in terms of which elements of the regular expressions it wants to match against a piece of the string. And so this sort of holds true for any NFA implementation of regex that employs backtracking. And so this is true for Perl, this is true for .NET, and this is true for Python and a number of other languages. So now you might be asking, an NFA? What is an NFA, right? An NFA is a non-deterministic finite automata or a finite state machine. I'm not going to teach you what an automata or a finite state machine is because I don't understand it that well. But the difference between what we might call a non-deterministic and a deterministic finite state machine is that in both cases we have some input that we're feeding into this machine. The machine is in some state. This is why it's called a finite state machine. And for each input that we give it while in a certain state, it will transition to another state. The difference between an NFA and a DFA is that an NFA can have superpositional states by remembering what the last state was, and this is how you get backtracking. This is great for things like ambiguous matching, this is great for backtracking, and this is great for recursion. The alternative to this is known as a deterministic finite state machine. This was how grep set was originally implemented. My impression is that this is partly how the regex parser or the regex engine in Go is implemented as well, which is why you have some limitations there. And so in this case, the machine can only ever have one state, right? It's not like, oh, based on what happens next, I'm either in this or that state. They're extremely efficient, but they're also kind of inflexible, right? If you have to be able to describe any next possible state based on any next character that you read as input, you're going to end up with a huge finite state machine. And so this means that they can't do lookbacks, they can't do nested expressions, and these sorts of things that we're going to have a look at that we can actually do in .NET. So, okay. So I've been talking about these finite state machines. I've been talking about regex kind of in the abstract. A few examples. This probably still doesn't make any sense, right? So, like, seriously, what is this sorcery? What I've tried to describe here is an example from the Microsoft Docs page for backtracking in the .NET regex engine. And on the left-hand side, we have a regex pattern. We can try and go through it. It looks for the character E 2 times. This is known as an absolute quantifier, right? So we're looking for 2 times E. Then we're looking for \W, which means a word character. A word character is either a letter, a number, or an underscore. And then finally, we're looking for something that we describe as /B. B stands for boundary, and so what we're looking for here is a word boundary. We're looking for a position in the string where we have a word character on one side and a non-word character on the other side. So right, like the end of a word. On the right-hand side, we have a string needing a read, and what I've tried to kind of visualize with these 2 arrows here is a sort of cursor or a sort of memory that the regex engine needs to keep track of. So here at the first letter in the string, we can't really match E. Okay, so we jump to the next position. All of a sudden, we have a partial match. The first E in our pattern matches the first E in the string. Okay, so far so good. Now, the regex engine itself will keep track of a third pointer or a third cursor. We're going to forget about that for now, but just know that there's a little more to keep track of here. Now, the next thing this pattern needs to match is it needs to repeat itself one more time. We need 2 instances of E. So we ask it to look forward in the string. Ah, great, our partial match got even bigger. All right, so next step, we need to find a word character. Ah, turns out that the next character is also a word character, so far so good. We almost have a match, we just need to figure that last one out. So when we jump to the last element of this regular expression, a word boundary, and we then look at what's ahead of where we are in the string right now, this position right here, between D and I, is not a word boundary. Because we have word characters on both sides of it, right? We're in the middle of a word. That's too bad. You know why Joey's sad? Because it's time to backtrack. And this is a costly operation. Now we need to remember where we were in the pattern that we almost kind of matched, and we also need to remember where to start over from in the string that we were kind of passing through. Because if we go back to the start, we can do this over and over and over again, right? We're going to end up in a loop. So where to start from? Remember that second cursor I told you about? The last time we started matching something else. Okay, so we jump to the next character after that cursor. See, Joey learns stuff all the time as well. Okay, so we start over from here. Once again, pretty good, right? We have a partial match. E matches. D is not an E, and so now we have a problem again. Joe's back. He's crying now because we need to backtrack again. So we backtrack one more time. Back to the start of the expression or the sub-expression that we're currently looking at. And so the next character is D. Okay, that's not an E. Neither is I. Neither is N. Neither is G. Neither is a space. Neither is A. Space is still not an E. And R is not an E. Ah, now we're getting somewhere. So once again, we have a partial match. The first E, starting to look pretty good. We get 2 E's. We have a word character. And finally, because the end of the string is here, we can now satisfy the very last condition in this expression, which is that there's a word boundary at the end. It's pretty cool. So what happened with that Stack Overflow bug? What happened was that this regular expression at the top had been in place forever, right? They had been using this for years. The thing they were using it for was trimming a post or the summary of a post so that they could display it elsewhere on the site. And so this had been in production for a long time, and it seemed to work just fine without too much overhead. The problem is that someone went ahead and posted an answer in which the content looked a little bit like this. There's a bunch of white space at the start of the post. Then there are some words, some non-space characters. Then there's a lot of white space characters. And then towards the very end, there were some non-white space characters again, before the final white space. So that means that this pattern at first is going to succeed in stripping away all the white space at the start of the string here. But before it can get down to the bottom and kind of trim it from the end, it needs to go through this entire block of strings, right? So I don't know how many spaces I have here, a few hundred maybe. In the input that caused the outage, we were talking about 200,000 white space characters. And so what's going to happen here is exactly the same thing we saw before, is that the regular expression engine is going to recognize that the right hand of this alternation, one or more white space characters, can start partially matching right after end. It's going to go all the way down to the last non-white space character, and then it's going to say, I can no longer satisfy that this should be the end of the string. Let me just backtrack to one space after the first one I tried. And since you have 200,000 white space characters, it's going to do this 199,999 times. And that's going to take a long time and a lot of CPU cycles. I hope this visual device maybe was a little better at explaining what actually went on in this outage. I've stolen all of this blatantly from Mark Minassi with permission. All right. Now we've had a look at me mucking about in PowerPoint for long enough. So what we're going to do instead is we're going to jump into some demos. Has anyone here seen me give this talk? Yes? Oh, yeah, absolutely. Is this better? Bigger? Yeah? All right. So if anyone has seen this talk before, either last year or the year before, a bunch of these examples will be kind of repeat offenders, but we'll have some interesting stuff at the end. But okay, what can we use these regular expressions for, right? And so, as I said before, I'm kind of addicted to Stack Overflow because people ask interesting questions, right? They pose interesting problems that, okay, they're kind of fun to muse about how you could solve. And some of these problems either ask explicitly about, can I do this with regex, or they ask problems where regex is kind of right up the alley for sorting these problems. And so this is sort of a classical example. I have a list of strings. They might be identifiers. They might be conjoined identifiers. We don't know. We have this list of strings that contains letters, and then it contains some numbers, right, some digits. So if I define this string, what we want to do here is we want to sort these alphabetically first, and then we want to sort them by number. And so it turns out that sort object in place of a property name takes a script block. So instead of a property name that references whatever we just piped to sort object, we can start doing some interesting stuff inside this script block instead. So if we take our list of strings, pipe it to sort object, and then specify that the first property we want to sort on is the string itself, but a version where we've replaced all /d. D stands for digit, so this means that we're going to remove all digits from the input string and then sort by that. And then finally, the second sorting property is going to be a version of this string where we've replaced anything that isn't a digit. So we end up with just numbers in the string that we sort by. So if we try and do this, and then scroll up a little bit here, what you're going to see is that it correctly sorted alphabetically first, right? We have all the entries where there's only a single letter A at the top here. Then we have AA and then AB. But something's off here, right? Apparently, 111 is now less than 22, and 101 is now less than 11. This 10 and 9, this doesn't seem right. So the reason for this is that if we just strip away anything that isn't a digit inside of a string, we still have a string. And so PowerShell is going to try and sort it alphabetically, and sure, 1 comes before 9 if you try to sort it alphabetically. So what we can do instead is, in the second property, we take the version of the string that no longer contains non-integers or non-digits, and then we cast that to an integer, and this will cause sort object to interpret this string as an integer, right, and sort it numerically rather than alphabetically. So if we try this again, we see that now the first property still holds true. It sorts alphabetically first, and then finally it sorts numerically. You can similarly do this with group object, right? If we want to figure out if any of these have a similar number but a different string, then we could use group object and similarly pass in a script block rather than a property name. Now, where regex and where regex in .NET specifically becomes interesting is that we can also do some other things than just saying I want to match a single digit or I want to match one or more digits, right? So here's a case where someone had ended up in a situation where some data, some coordinate data had been removed from a CSV or whatever format it was in, and then it had been joined by a dash. I mean, this is great when you have two coordinates like 8 and 12, but it's not so good when you start getting into signed or negative numbers, right? Because if I take the first of these input strings and I split it by dash, sure enough, I get the result I want. I get the first value 8, the second value 12. But if I try to do this on the second string where we have negative integers, we're going to see here that partial seems to output an empty string, 4, 2 more empty strings, and then 2. And the reason it does this is that it says, oh, I must split right here, so I'm going to give you the empty string before anything else. Then I'm going to give you the 4. I'm going to split here again, give you this empty string, split on this again, give you yet another empty string, and then finally you get 2 back as the very last argument. So how can we do this in a backtracking regex engine? Well, backtracking regex engines have this have some constructs called look-behinds and look-aheads. And so basically what we can do with look-behinds and look-aheads is we can describe a position in the string, right? We can describe a position in the string of no length. It's 0 characters wide, but we can describe what happens right behind that position or right after that position. And so in this example, we're going to use a look behind. So instead of just splitting on a dash itself, we only want to split on this dash if the preceding position here itself is preceded by a digit. And so this construct right here is the look behind. What we're saying is that right behind here, you should see a digit, otherwise don't match this. And so if we do this instead, we're going to find that it still works, because that's the case in the first example. But in the case where we have negative integers, we now get the correct result, and it preserves the dashes because it recognizes that it's actually part of the number. Right. So and now that we're a little bit more familiar with the magic of these look-behinds and look-aheads, in the interest of time, I'm going to skip some of these more simple examples. If you want to see me go through these examples at length, I suggest you go through the code when we're done here. But there's also a recording from PSConf EU from 2 years ago where some of these same examples are gone through in a little more length. So one thing I do want to go over again, because this is something that that trips up a lot of people, is what about emails, right? Surely that must be a job for regex, right? I have a potential email address. Maybe I want to do some input validation. Maybe in my partial function where I need to send an email off to someone. Isn't that a job for regex? And my answer is absolutely not, and we'll see why. So the kind of simplest, almost correct email validation pattern I can come up with is this. And I don't know about you, but I don't find this particularly readable. And this is like the simplified, incorrect version, right? Because if I try to define this, and then I define something that might look like an email, but it's not actually a valid email, and then I'm going to define something that is actually a valid email address, even though it might not look like it, kind of the two extremes here, and I try to match that against our regex-based email validation, I'm going to get the incorrect answer for both of them. Now, I could also have expanded this email validation regex so that it would take a lot more into account and actually be correct. The problem is that the nearest we've ever come to that is a beast like this. And so this is, I think, 6,000, around 6,500 characters in order to describe what an email address looks like. And yeah. So this is like the horror example of what not to do with regex, right? And rightly so. If you put this in your code base and a coworker comes by, they're like, "What this? It says email, but it has nothing to do with email." Right? Yeah. Don't worry about this. Yeah. Say that again. Right, imagine if you put these 6,500 characters into the argument for a validate pattern in your function parameter signature, right? Like, I would open that function definition file and go like, nope, elder4. Right, so, huh? Oh, in the regex, yeah, I'm sure of it, yeah. Right, so, what can we do instead? It turns out that the regex is not actually very good, and also all of these nesting constructs in this 6,500 character correct email validator are also going to be extremely slow for some of the reasons we already discussed. So what can we do instead? Well, it turns out that .NET has been around for a long time. .NET is filled with a bunch of classes that comes in something called the framework class libraries that we can use to do all sorts of interesting stuff. And so one of these, and there's a type accelerator for this in PowerShell, is called a mail address. And so something that might be both faster and easier would be to just try and cast our actual email address to a mail address object. And if we do this, we're going to find out that it succeeds. Okay, maybe this is a better validation. So I suggested this on Stack Overflow, I think, as an answer to a question, and someone pointed out that even mail address actually has some flaws, right? It has some things where if you do a double dot in the host name, it'll actually validate it, so maybe it's not the most perfect thing. And so the argument he was trying to make is that straight back to the regex, right? Like, this is terrible. Now I need to look for a dot in the host name. I will use that 6,000 line or 6,000 char regex. I would propose that if you get to a point where the only problem you have is hostname specific, that's going to be way easier to inspect than the email address as a whole. And so what you can do when you cast and assign this string as a mail address, and check this is going to be true. What else can we do with it? Okay, if we look at this.
Sorry, can you explain the syntax you're using in line 178 and 179?
Yes, absolutely right. Okay, so what I'm doing here is this is a cast, right? I'm taking that string that's held in an actual email and I'm casting it. I'm asking PowerShell to attempt to convert this to an email address, right? Whatever output may come out of that, because that's going to output this new converted object if it succeeds. I'm going to assign that to null because right now I'm just interested in whether it fails or not, right? After this, what I can do is I'm going to inspect dollar question mark. Dollar question mark will hold the result of the last statement executed, and so that means that if this for any reason fails, the statement immediately after where I reference dollar question mark is going to be false, right? So if we enter this block down here, it means that the cast up here succeeded. So does it work? All right. So the question is, what else can we do with this mail address object if we want to do further validation or inspection of this? Well, if we look at this mail address and pipe it to get member, what we're going to see here is that it has a number of properties: address, display name, host, and user. Interesting. So if I look at mail address, user, okay, that was the user part. Makes sense. If I look at host, it's kind of hidden because of some Unicode rendering bug here. There is a dot in here, and so here we get the host name. And so what can we do with this? Well, you can't look up this name against DNS because it has a Unicode character that signifies a phone in it. But what you can do instead, now that you have this primitive string that tells you what host name it is again, the .NET Framework class library to kind of to the rescue here. It comes with a class called an IDN mapping. IDN mappings are used to convert between non-ASCII DNS names and then what we know as Punycode, which is kind of a representation of Unicode that you can use in DNS. This is how web addresses with weird squiggly characters and Scandinavian domain names and this sort of thing work. So if we create a new IDN mapping, we can use this object to get ASCII on our Unicode string. And so we're going to pass in mail address host. And we're just going to see what that leaves us with. And so now down here, it resolved the actual DNS name represented by this Unicode string up here. And so now we can do interesting things like looking it up, seeing if there's an MX record for this host name, right? And so now you can actually start doing contextual validation on the input that you got, if that's what you want to do. Again, I'd say that this is probably more reliable and more readable than, again, 6,000 chars of regex, right? Right. Yeah. You could split the string at the @ sign. What if I feed you a string with more than one @ sign? What happens then, right? So there's a bunch of complexity in there. So combining these two approaches where you say, let me first try to cast it as a mail address, and then if you have specific requirements for what the hostname looks like, if you don't, let's say, accept plus signs in the user part, you can do that with regex, but it's way easier to do that with the individual parts of the email address than the entire email address itself in a single expression. Right. So this is all fun. We can do a lot of stuff with regex, but where it gets more interesting is if we can generalize some of these patterns, right, and kind of turn them into reusable tools. And so someone asked, can I get like a find and replace special characters thing in PowerShell? He had some string input that might have some special characters that he wants to strip out of it. And so he came up with a simple function like this. The regex pattern that we've defined here is, again, ankle brackets, so any of the elements in here. We're looking for, I think this should actually be escaped. We're looking for a £sign. We're looking for things like question marks, opening brackets of all sorts and closing brackets again. And then we want to replace them with a certain pattern, right? So we apply the replace operator. And so what we're going to see is that if I say replace special chars, and I give it an input string of hello there, it's going to replace all the squiggly characters, regardless of whether it was one way or the other, with a replacement pattern. Now, this might be useful for this specific question, right? The specific problem that this guy was trying to solve. But it's likely that he's going to run into a situation where he gets input from elsewhere, and he needs to strip out other special characters. So what I like to do whenever I write any of these sorts of small functions is to try and write a kind of generalization for it so that you can actually reuse it elsewhere. And so a good example of this, kind of showcasing some other regex primitives, is if we do a generalized version of this replace special chars thing. We're still going to take an input string. We're going to parameterize the replacement. Maybe it made sense with _a there, but probably not everywhere. And then we're also going to parameterize these special characters that we're going to use in our replacement pattern. And what you'll notice here is that, unlike up here, I don't have the square brackets around, and I don't have all of these backslashes all over the place. And there's a good reason for this, because what we're going to do is we're going to convert this string of these weird special characters to a character array. We're going to iterate over them, and then we're going to call regex escape. And as soon as you call regex escape on a string or a character, it's going to take that, it's going to have a look at that string and then say, one of these characters is a meta character, like if you have a dot or a star or the end of string $sign, and it's going to escape that for you. So you don't need to remember what do I need to escape, what is the order of this, how many backslashes do I need. You can kind of just defer all of this to the regex engine itself. And then finally, we're going to join all of these with an alternation. So what we're saying is, look for this or this or this or this, and as soon as you do that, you've matched and we want you to replace, right? And so up here, if we do replace special chars again, and we give it the same input string, and then we say that the replacement is going to be u. Let's do something else. Let's put a dash in there. And then finally, the only special chars that we want to match is the closing parenthesis. Now we see that whatever regex pattern it constructed included only the closing parenthesis, and therefore these ones are left alone. If we try this again and put some more strings in here, maybe one of these, you're going to see that once again it left this one alone because we overwrote this parameter with a custom set of characters. And so this means that he can now reuse this in places where the syntax or the grammar of whatever the input is different from what he expected in that first place. I am formally required to start the Q&A now. Does anyone have any questions, or do you want to do more regex examples, or are we all falling asleep? More regex? Yes. Is this true? Okay. Your funeral. All right. All right. Right. So one of the last examples I gave the first year we did this is that you can use some of these grouping constructs, and especially these look-behinds and look-aheads, for some pretty crazy stuff in regex. As you try to scale some of this, it's not going to be terribly efficient, but you can do some interesting stuff on small strings and small terms. So basically, the question: how can I test if an input string contains any of X substrings, right? So here I have a string with some words, and the only thing I'm interested in is whether one of 3 specific words occur in the input string. So what I'm doing here is, this is a non-capturing group, so this is just a grouping of strings. I expect it to be bounded by word boundary on both sides, and then containing either word 1, word 2, or word 3. Fairly straightforward. Okay, so this is true because word 2 is certainly contained in here. Now, how can I test if some input string contains all of X substrings, right? Maybe I have some requirement that certain terms pop up in a certain string. So the input string this time has both the word 1, word 2, and word 3. Once again, I'm just going to look for a word boundary. The first word, anything, the second word, anything, and then the third word. To do this properly, I probably should have added word boundaries as well. We can do this here. But in any case, this is going to return true as well, right? We found both word 1, word 2, and word 3. But what if I need to figure out whether they're in there in any order? This string down here also has the term word 1, it has the term word 2, and it has the term word 3, just like before. But this time we've shuffled up the order, right? There's no saying. And so if I try to test this again, this kind of naive approach of having the word, anything, another word, anything, and another word, it's going to return false, even though all 3 of them are in there. This is where some of these ser-length assertions or these look-aheads become extremely valuable. Once again, here the question mark and the equal sign means a forward look-ahead. And so at this position, right after the start of the string, what I'm expecting to find following that string is anything, and then my bounded word. Then at the next position, which happens to be the same position because this describes a place in the string that is exactly 0 characters wide. So at the exact same position, I also expect to find anything and then a bounded word 2. And similarly, at the same position, I'm expecting to see anything and then a bounded version of word 3. And then finally, something and then the end of the string. And so if I try to do this now, notice again, the words are in the wrong order, but the right words. It now returns true. Again, what you might want to keep in mind here is that this might not be the most efficient things, especially if you have nested sub-expressions after your look-aheads in a pattern like this. But for a few terms, like 3 or 4 against input strings of limited length, this shouldn't be a problem. So one thing you could use this for, and I feel kind of bad as a security practitioner saying this, but up until very, yes?
Performance benefit you get by converting a greedy regex into a non-greedy regex, or how you can improve the regex by including the initial position marker or the final position marker.
So I didn't get the first question. Converting between which types of regexes?
When you get a greedy regex and you, as the example showed earlier, you can really simply optimize it so it's a non-greedy.
Oh, absolutely, absolutely. We'll do those in reverse order. So the second question asked was what is the performance benefits of using these anchors, right? These start of string, end of string anchors, for example, or these positional anchors. Well, the nice thing is that as soon as you see a pattern that's anchored by at least by the start of string anchor, and then I do something like this. This means that the regex engine knows that this sub-expression can only match from position 0 and forward, right? So that means that if it gets to character 8 after the start of the string, and the expression does not match, it can give up completely and just say it did not match, right? So that means you can basically return early from passing through the entire input string. With end of string, I'm not actually sure how that is implemented in the regex engine in .NET, because again, all of this is forward read over the input string, right? So you can't really guarantee when is the end of the string going to be if you do it over a large string. But I imagine that you get a similar performance benefit, because if you have a string of length n, then it doesn't make sense to do it from the start if the pattern itself is not possibly that long, right? The other question was greedy and lazy matching, the difference between that? Right, okay. So greedy, I think I mentioned on the partial performance slide before that some of these adverse performance effects that we see of certain regexes against certain input strings has something to do with greed, right? And so greed in this context has to do with how many characters does the regex engine think that a element in your expression needs to match. And the rule of thumb here is that unless instructed otherwise, the regex engine will always try to find the longest matching substring that matches anything, right? So that means that if I do something like A star, this regex pattern, right, and I give it the input A lot of times, then the expression over here, even though it says 0 or more times, is going to match that entire string of 12 A's, because it tries to, as I said, get the longest matching substring that it possibly can. And this is also what then causes stuff like backtracking, because this could have been satisfied at position 0 or at position 2. But now, if we have something after here, now we need to backtrack a couple of times before we can satisfy the last 5 A's, which is then going to take up basically the last 5 characters of this string, right? A way of showing how this impacts performance adversely is, I think, the classical example goes a little bit like this. I'm going to describe a string, again, consisting of a bunch of A's. String. I'm going to repeat this string A 20 times. Then I'm going to construct a pattern that validly describes this string. Let's call this regex. And what I'm going to do here is I'm going to say that it should match A, maybe or not, 0 or 1 time. I'm going to do that 20 times. And then I'm going to add something. I'm just going to add 20 A's. And so now, I have my string, and I have my regex. And so this regex down here is absolutely satisfied by the string. Because again, the question mark quantifier means 0 or 1. So that means that the first 20 characters A here could match 0 characters in the string, and that would still be valid. After which these 20 characters A would then match the rest of the string. But that's not what's going to happen here. What's going to happen is that a question mark is going to match the first A, because by default, again, it's being greedy, right? It's trying to get the longest matching substring that it can. And so if we try to generalize this a little bit, invoke regexterror. So what I'm going to do here is I'm going to define a small little function that takes a single parameter that's going to be an integer, and this integer signifies how many times we're going to repeat the A, both in the pattern and the input string. And so I'm going to count here, count there, the same thing here. And then finally, we're going to do measure command string match regex. And then we're going to output some object that will tell us the total milliseconds from that measurement. How long? This is a valid property name in PowerShell. As is this. And so we're going to feed the count in here, right? So if I define this function now, and I say invoke regexterror count 10, it's going to return pretty quickly, right? This took 4 milliseconds, right? If I do this with 20 characters A, right? Like we're talking about a string that's only 20 characters long. All of a sudden it takes 45 milliseconds. What happens if we bump it up to 25? Oh boy. Over a second to match a relatively straightforward pattern against a string of 20 characters, right? Over 1 second. I'm not going to do this because we're going to run out of time in a second, but we probably would if the Q&A was half an hour either. Let's bump it up too. This is again the effect of the regex engine trying its best to be as helpful and as greedy as possible, and then figuring out at the end of where it can't match anymore, oh, I need to back up. Let me try just one further. And again, this is going to keep on going and going and going. So here we start to see some serious exponential growth, right? We went from a string of length 25 to 27, and all of a sudden it takes 4 times as long to match this completely valid string against our pattern. Yes?
So now I have to ask, can I force my PowerShell to use deterministic regex?
No, you cannot force the regex engine to have a different nature than it has. What you can do instead is you can modify the behavior of the patterns that you write. So one thing you can do, if you recognize a pattern like this that is susceptible, what you can do is there's a grouping construct that looks like this. If you do greater than angle bracket here right after the group construct opening, and then you put any pattern here, what's going to happen is that as soon as you get a partial match of that sub-expression, this tells the regex engine, if you get a match for this, don't ever track up further behind than where I am right now. So this way you can kind of say to the regex engine, stop backtracking further than till here. I'm having a hard time coming up with like an example that would like show this, but there are ways of basically instrumenting the regex engine to say for this specific sub expression, please stop this behavior that's making everything slow. There is also guidance on Microsoft. Yes. Can I put what in my function? Yes, so I can put this in my function, but what is going to happen when I kind of disable backtracking, if I do that for the first part of it, the A question mark, A question mark, A question mark, is that since I disable backtracking, it can no longer track back and it's going to fail. So it's going to tell, yeah, no, it doesn't actually match, even though it technically matches. So there's some problems there as well. Rather than me standing here talking about something I don't know, I'd suggest you go to Microsoft Docs. There's some pretty up-to-date documentation on backtracking behavior in the .NET regex engine. I'd very strongly recommend you go have a look at that. It also comes with some guidance on how to recognize some of these patterns that, because of their greed or because of their nesting behavior, are prone to this sort of terrible behavior, or this sort of terrible runtime performance. There is some guidance for both recognizing and how you can rewrite it in a way so that you don't end up with this sort of catastrophic backtracking. All right. Jabe said P is not for you as well. All right, summary. What is regex? Regex is a meta language, the syntax of which varies a little bit from different languages, but they kind of all look like each other. Regex engines are non-magical Turing machine generators. I don't know what you're going to use that for, but now you know. A lot of good use cases exists, but the pitfalls are also real, and so please apply in moderation. As always, slides and demo code will be up here. Any other questions? Yes?
Can you explain the regex that you have on your main slide?
Oh yeah, I forgot about that. So the question is what was the subtitle of the joke that I put on the first slide? And so I'm not going to scroll back through the whole Turing machine here. So basically, the first group, first we have an anchor, right? We have the start of string, the caret. And so at the start of the string, what I'm expecting is a grouping construct, a named capture group called PP. Inside this capture group, I'm expecting the character A and a space. Then I have the question mark that basically says this is optional, right? Either 0 or 1 occurrences of this group. Then I have a string, must have tool. And then finally, I have a sort of weird grouping construct down here that's not actually a grouping construct. This is known as a conditional. And this is something that a few languages implement. I'm pretty sure you won't find this in JavaScript, Go, and a number of other languages. But basically what this means is that if this capture group PP exists, like did we actually capture a space, look for nothing. Otherwise, look for an S. So this particular regex is going to match two distinct strings. It's either going to match a must-have tool or must-have tools. Yeah, thank you for reminding me. All right. If there are any other questions, feel free to grab me here or tonight or throughout the conference. My name is Matthias, and this was Regex 4.0.